So welcome everyone. This is the 20th webinar in the discussion series on tipping elements, the notion of irreversibility and abrupt changes in the Earth system. My name is Thomas Lontzek, and I'm a professor of economics at RWTH Aachen University in Germany. So while we are still waiting for some audience to join this meeting, please allow me to say a few words about this discussion series. So the goal of this discussion series is to advance knowledge on tipping elements and to support efforts to increase consistency in treatment of tipping elements in the scientific community. Furthermore, we plan to develop a research agenda and design joint experiments and ideas for a tipping element model intercomparison project, TIPMIP. And so there are a few networks behind this series. So we have the Earth Commission and AIMS, the Analysis, Integration and Modeling of the Earth System project. And both AIMS and the Earth Commission are hosted by Future Earth. We also have the Safe Landing Climate Lighthouse activity of the World Climate Research Program, WCRP, of which I'm also a member. And this event is co-organized by the International Institute for Applied Systems Analysis, IASA, and the PIC, the Potsdam Institute for Climate Impact Research, and the Global Systems Institute at the University of Exeter. Okay, so the focus for today is on economics' view of tipping points. And we will hear talks about how to incorporate them into cost-benefit analysis and economic projections. Now we will have two speakers today, and they will present before we have a Q&A session. So, however, during the talks, please feel free to pose questions and indicate maybe to whom your question is directed to using the Q&A feature at the bottom of the Zoom window, so that everyone can upvote the preferred questions. And we will then get to these questions in a discussion session following these presentations. And furthermore, following this event today, we will post the recording online and the slides on the Tipping Point Series Confetti webpage so that they will be accessible in the future. Now, let's get to business. Our first speaker today is Anne-Sophie Crépin. Anne-Sophie is based at the Beijer Institute at the Royal Swedish Academy of Sciences. She's also a principal researcher at the Stockholm Resilience Center, and her research focuses on the interplay between economic incentives, ecosystem regime shifts, policy, and human behavior. Her research links scientific theories about the Anthropocene, regime shifts, and the economic dynamics. And also most recently, she has also focused on empirical studies and behavioral experiments. Anne-Sophie, thank you very much for being here with us, and the floor is yours.
Thank you very much, Thomas. So I will start sharing my screen so you can see what I will present. Do you all see what I'm showing now?
Yes.
That's great.
Great. So today I will talk about some recent modeling and experimental advances that we have made, not only me, a whole group of researchers have made during the last 30 years. Let me just move the bar here because it's disturbing. Yeah. So the presentation I will give today is based on a review article that we have just got accepted for publication in a scientific journal. And the outline of my talk will deal with how to model thresholds and regime shifts, so that we know a bit how we do. The management challenges associated with tipping points and how to deal with risk and uncertainty. And are tipping points a motive for precaution? And also, finally, so I will give you some results of behavioral experiments with tipping points. And all these are elements that are found in the economics literature related to tipping points that have been exploding recently. It's really a growing literature on economics and management of ecosystem with regime shifts and tipping points. And there have been many reviews published on the topic, but since the field is changing all the time, there are new things popping up that merit attention. So some ways to model thresholds in the literature. Basically, I mean, there are several ways, but basically the main ways that have been used a lot are these three ones. So you may have a change in the some variables that happens after a threshold, and that change can be smooth, going from a low level here of the variable to a higher level after passing a threshold, and you see that here the change is smooth. In the limit, when that change becomes less and less smooth, you get a shift, a sharp threshold, I would call it, a shift in variable, a jump in a variable. You also have a very another way to present threshold that has been present in literature for many years, since at least the 1970s, which is the dependency in fisheries model, for example, where the threshold is a space where you have too low population densities to allow mating of population, which means that they do not grow, they start decreasing instead. So these are the three main ways I would say that you can find in the literature. This way of modeling threshold here can be modeled with some particular equations, and they differ a bit depending on whether they have been used in climate models or in ecosystem models. Here's how these different models that have been seen in the literature when it comes to ecosystems more than climate, because I suspect that Simon will talk a lot about climate. So the most known models are the ones that deal with lakes and bodies of water and deal with pollution in these lakes. And the two main models that have been presented in the literature make use of these different types of threshold, the more smooth one or the sharp one. And common to this model is that they model a flow of nutrients in a lake or in a water body. It could be a fjord or a river. They have an outflow of nutrients from that water body. And then there is a threshold term that you can see here or here, which basically models some sort of release of nutrients from the bottom sediment of the lake or the water. So when there is a lot of sediments in the water column, then the bottom sediment does not absorb the nutrients anymore and start releasing them, which creates something threshold and tipping point. So that has been one way to model them. And this has been used a lot in literature. We have also several models of resource exploitation in the literature that deal with mostly fisheries, but also forestry. And these models typically use logistic growth. That's a term where you have a growth of the resource that is quite traditional, has been used a lot in economics. But they add another term that makes it, that introduces a tipping point. So you have either this term here, for example, that is called the holding type 3 term that represent predation. And it's symbolized here in this coral reef, for example, with a situation where the coral could provide protection against predation, which can influence how much of this term can be influential on the dynamics in the coral reef. It can also be, in this case, in the second case here, the resource growth with dispensation can be representing, for example, schooling, when fish species tend to gather together in big groups to where they can mate easier and so on and so forth. If the fish end up outside of these big groups, then it's more difficult to find mating partners, and they can't reproduce anymore. So then you have some sort of threshold dynamics there as well. So why do we study these thresholds in economics? Well, because they present some management challenges. And I would say that the main challenge comes from the fact that once you have thresholds in the system, you introduce some sort of history dependency. So what will be an optimal management will depend on what has happened in the past. And depending on whether you start with a eutrophied lake, for example, or a clear lake, you will want to end up when you manage it, you may decide to go back or to stay in a clear lake, or you may actually choose to stay in a eutrophied lake because it may not be worth trying to clean it back, or you have other uses of the lake that imply that you may need to actually pollute it. So this kind of history dependency creates a couple of challenges. The one was raised already by Weissman in 1974, which implies that the price regulations, the taxes, may not reach efficient resource allocation simply because there are discontinuity in the state space when you try to manage this system, which means that you can't just use one tax or one price and think that you will solve your optimal management system. You may have to do something else. And there is a couple of researchers, Heijer and Heinen, in several papers have studied these problems, and they have shown, for example, that when you have this kind of problem and you are in the wrong regime, you want to go on to pass the tipping point, the best type of policy in this situation is to apply cold turkey policy, as they call it. You put a large shock for the shortest possible time to push back the system to the desired regime. So that's illustrated by this, like pushing quickly that poor woman across the threshold so that she ends up in the other regime. And then once the regime has shifted, you can apply a traditional policy like a standard tax that is high enough to keep the desirable regime that you have. Another management challenge that was raised by, for example, Arrow and co-authors is related to how to evaluate policy reforms, to cost-benefit assessment and these kind of tools that we use a lot in economics. And when you, in most cost-benefit assessment, you can base your assessment on marginal assessment. So you can see what happens if you increase something very slightly, will it be both beneficial or not? And then you can base your decision on that. But when you have tipping points, then you may not be able to do that. You may actually have to investigate what are the full benefits and costs of the policy in place, which requires much more information to be able to get good answers. Another issue that pops up when you look at tipping points is that in general, it's not, you don't have full information. There is a lot of uncertainty related to that. And there are a lot of different types of thresholds related to tipping points. So the one threshold that we are the most familiar with are the one in the ecosystem itself. So that's the nutrient threshold between a clear lake and a eutrophied lake, for example. But when you put management on it, then you get another type of threshold, which is called Skiba point or Skiba indifference threshold, which shows where society would be indifferent between going to one situation of the lake or the other situation of the lake. So in this, if you start on this side of the Skiba threshold, then you would prefer to go to the eutrophied lake. But if you start on this side of the threshold, even if you're already in your eutrophied lake, it may still be beneficial to actually shift to the clear lake. So that's another type of threshold. And the third type of threshold pops up when you have uncertainty involved, because then you may not know where the threshold is, but you may have some knowledge about where you're sure that you're not passing the threshold, and that would be called a risk threshold, a situation where you're sure that you will not pass the threshold. And that is an important threshold to know in situations where the optimal policy would be to actually be careful and not be sure to not pass the threshold, to have some safe management policy in place. Another element that has been studied a lot in economics is how to specify the risk structure when you have thresholds. And there are two main ways of doing that in the literature. One is what we called time-distributed catastrophe. So you have a hazard rate that shows the probability of a catastrophe happening at some point in time, and it's time dependent. So In this situation, it's a bit like a dynamite with a fuse. You have a fuse that may be more or less long, but you know that once it's lit, it will explode at some point. You just don't know exactly when. So, and that's a way to model risk in this type of tipping point problem that is really pervasive. It's happened a lot. Another way to model risk is what's called state space distributed catastrophe. Here, the risk is dependent not on time, but on where you are in the system. And if you know that you are in a safe space, you know that you will stay safe there forever. And then you can move around in the space. If you come to an unknown place, you can hope that you're not trespassing the threshold. If it turns out that you're not, then you know that that space is safe. If you're trespassing the threshold, then the catastrophe happens and you can't go back. But that's not the entire picture. If you look at a lot of environmental problems, there is also something called inertia that is in place. So what happens is that things can accumulate, which means that you can have change that doesn't seem to change anything. You can have accumulating pollution, for example, that doesn't seem to change anything in the system. But then suddenly it releases some sort of inertia, and then you get the tipping point happening much later. And this implies that you need to model things a bit differently. And my co-author and I, Erik Nevdal, we did a paper on that where we introduced a second equation in the addition of a hazard rate that is dependent on state, but also on stress. And the stress dynamic would be a bit slower, which means that it can accumulate and release these tipping points. So once you have uncertainty and tipping points, a natural question that comes to mind is, should we be careful? And there are different types of responses to that. So for example, now at the moment in Sweden, it's freezing. So the ice on the lakes are freezing, but you may want to be actually precautious to not stamp on the ice too soon so that you don't want to go through the ice because it's too thin. So that's one way of, so then you wouldn't want to be safe and precautious. But you may also, in other situations, want to not forego opportunities. And in this situation, so this is from the Hitchhiker's Guide to the Galaxy, where you are the end of the world happening, then there is a restaurant at the end of the universe watching the end of the world happening, because why not have fun while you know that the resource will disappear? You may as well exploit it very much before it's gone and have fun on the way. So the question has been asked in a lot of settings whether we should be precautious or not in exploiting resources with tipping points. And the answer is it depends. So there is a seminal paper by Polasky et al. That also puts a lot of perspective on early studies that were only looking at stock collapses. And if you contrast the collapse of the stock with a more simple change in system dynamics, you get different situations. But it also depends on whether the probability of the shift would be can be influenced by management or not, whether there is diminishing returns in the resource that you study, or whether there is present bias that will influence whether you should be precautious or increase exploitation when there are tipping points. So it's not a clear answer. And now I will go to the last point of my presentation, which is about behavioral experiments, because all these results so far pertain to optimal management, but in the world we are managing resources collectively in ways that are not necessarily optimal, because it's not always easy to do it. So then there are a lot of questions: what happens when you have tipping points and groups manage resources together? There have been quite a few behavioral experiments that look at these issues. So they put people together to manage a resource or discuss the provision of a public good. And these papers have looked at different factors that could trigger coordination or cooperation or hinder these aspects. And it seems that when you look at public goods, so the provision of public good, for example, cleaning of the atmosphere to minimize the risk of climate catastrophe. You see that factors that trigger coordination, for example, are a higher risk if the game is repeated. So if people get to make the same choice several times in a row, or if they get to communicate. On the other hand, the factors hindering coordination are uncertainty about the critical contribution. How much do they have to contribute to be able to hinder the catastrophe? If that's uncertain, it transforms the game in a prisoner's dilemma, and that may hinder coordination. And also heterogeneity among the participants is also a factor that may hinder coordination, but not necessarily. In common pool resource games, again, communication has been shown to facilitate sustainable resource use, and also the possibility to banish free riders. On the other hand, when you are uncertain about the threshold, it also may prevent sustainable resource use. But all these experiments are based on static resources or fixed resources. And together with my colleagues, Therese Lindahl and Caroline Schiel and Herman Tully and others, we have looked at what happens when we actually have resources that are dynamic, so that we have resources that can grow, and what happens when we exploit them, and there are tipping points in that. And we did that through a series of experiments. So these figures show the different types of resource growth that we show to our participants. So here you have the number of the amount of resource and how much it grows until the next period, if it gets to go there. And we have done experiments in the lab and in the field. We have tested both resource exploitation without threshold, with threshold, but also instead of threshold with a quota that would be placed at the same place of the threshold. And what we find in all these, I mean, there are a lot of nuances in the results, but a general result, I would say, is that when there are thresholds, it seems that people are more carefully exploiting in managing their resources. And we believe that it's because we allow communication to emerge, and when there is a tipping point, people start to communicate more. They learn about each other, knowledge about the resource, and then become better managers, and then they manage the resource more sustainably. So that's an interesting result, but it also depends on the context and how things change. And that we saw that a lot in the field. For example, Schiel and Rocha, they did experiments in 4 different communities in Colombia, and they could find the result we had in the lab in 2 to 3 of these communities, but in the 4th one, it was not possible to show the same result. So it depends on how the situation looks like. So this was my last slide. I would just give you some take-home messages before I leave you to Thomas and Simon. So overall, the literature has developed a lot, and the nuance about what to do with regime shift and how they can be modeled is much bigger than it was 30 years ago when this field started to explode. What we need for future research, I would say, well, what motivates precaution is still, it's been researched a lot, but there are still a lot of questions around the different situations that would motivate precaution or not. How do tipping points influence collective action in different contexts is also a big box of future research. But on top of that, I would also add how can we design policies that seriously take tipping points into account? I mean, there has just been very few attempts and not much yet. So that I would say would be something to look more into. Thank you very much for your attention.
Okay, thank you very much, Anne-Sophie, for giving us some insights into an overview of the work that you've been looking into. If anyone has questions, please post them into the Q&A box, and we will then address them during the discussion session following Simon's presentation. So now it's my big pleasure to introduce to you our next speaker, Simon Dietz. Simon is an environmental economist with a very huge interest in climate change and sustainability. He's based at the London School of Economics and Political Science, where he's a professor of environmental policy in the Grantham Research Institute on Climate Change and the Environment. He's also in the Department of Geography and Environment. He has published research on a wide range of issues and works with governments, businesses, and NGOs on topics of shared interest such as carbon pricing, institutional investment, and insurance. Simon, we are very much looking forward to your presentation, and the floor is yours.
Thank you very much, Thomas. Can you hear me okay?
Yes.
Good. Let me just share my screen. So hopefully you can see that now in full screen. So thank you again, Thomas, and thank you everyone for having me today. So I'm going to talk about the economic impacts of tipping points in the climate system. So in terms of how my talk relates to Anne-Sophie's, I'm going to be talking about the subset of tipping points in the climate system. And I'm going to be talking about trying to estimate the economic impacts of those rather than, for example, thinking about collective action in the face of tipping points. So in my experience of working on and talking about tipping points, it's incredibly important to try to get everyone on the same page at the beginning about what we mean by tipping points in the climate system. So forgive me for starting with some definitions, okay? And where better to start with the definition of climate tipping points than the 6th assessment report of the Intergovernmental Panel on Climate Change. So in IPCC AR6, a tipping point is defined as a critical threshold beyond which a system reorganizes, often abruptly and or irreversibly. So you can already see that abruptness and irreversibility are often attributes of climate tipping points, but not always. And there's further the question of what does abruptness mean in a climate context. So IPCC defines abrupt climate change as change in the climate system that takes place over a few decades or less, persists for at least a few decades, and causes substantial impacts. Okay. Lastly, I'll just throw in another passage from the IPCC report, which I think is important. Tipping points may involve global or regional climate changes from one stable state to another, or to changes that occur faster than the rate of change of forcing, and include shifts from one equilibrium state to another, and other responses of the climate system to external forcing. So to make this a little bit more tangible, I can show you a well-known graphic from a review of climate tipping points in Science last year by Armstrong, Mackay and colleagues. You can see a number of tipping points, or more accurately, tipping elements in the climate system here. They broadly divide into 3 categories. There are tipping elements in the cryosphere, such as the collapse of the Greenland or West Antarctic ice sheets. There are tipping elements in that are related to the ocean and atmospheric circulation, such as collapse of the Atlantic meridional overturning circulation. And there are climate tipping elements in the biosphere, such as possible dieback of the Amazon rainforest. So that applies the definitions I gave you to real world phenomena, and it gives us this class of tipping elements that you can see in front of you. So on the basis of those 2 slides, just let me make a few contextual remarks about climate tipping points. I think most importantly, I would say that climate tipping points are a heterogeneous class of phenomena. It includes things like nonlinear feedbacks and both reversible and irreversible phase changes. Okay, so we need to immediately realize that one particular mathematical representation is unlikely to do a good job of capturing the important dynamics of all of these tipping elements. And since that's the case, this heterogeneity makes it challenging to incorporate climate tipping points in economic models. It's going to make it difficult to find a representation which is going to cover all bases, as I said. what I also want to say is that in popular discourse, tipping points are identified with abrupt change on economic timescales. So when I say economic timescales, I'm thinking of years, even quarters. So part of the reason for that is the contribution of popular work like The Tipping Point by Malcolm Gladwell, which was a non-fiction book talking about tipping points in economic and social systems like white flight from urban areas. And those sorts of phenomena generally take place more quickly than the tipping of elements of the climate system. And some work in economics also reflects this more popular understanding of tipping points as being instantaneous events. Crossing climate tipping points may lead to abrupt changes on economic timescales or not. It largely depends on the tipping point. So with all that in mind, what I want to do now is give you a little review of the economic literature on the impacts of climate tipping points. I published a paper in 2021 in Proceedings of the National Academy of Sciences with James Rising, Thomas Sterk, and Gernot Wagner. One of the things we did in that paper was review the literature up to that point on climate tipping points in economics. And we came up with the following 3 points. Firstly, as you possibly not be surprised to know that most studies either ignored climate tipping points or had very indirect or partial coverage. So for example, if you are trying to build a deterministic model that contains best estimates of the response of the system to greenhouse gas emissions, you would be likely to overlook climate tipping points. But that isn't to say that economists have entirely ignored this issue, far from it. We found 52 papers that explicitly modeled the economic consequences of at least one climate tipping point. And that was we would have been doing this review in 2019 and 20. So that number will only have increased since then. But that's a considerable body of literature thinking about the economic impacts of climate tipping points. An important characteristic of most of that literature is that it represents climate tipping points in a stylized way, primarily by associating crossing a climate tipping point, such as a temperature threshold, with some kind of generalized economic catastrophe or disaster. Now, there are good and bad versions of this kind of model. Probably the best version out there is actually in the work of Thomas Lontzek, which I can show you diagrammatically here. So the idea here is that there is some kind of stochastic trigger point in the climate system, say a temperature threshold, beyond which an economic damage process is initiated. Now, what makes Thomas and colleagues' model a good example of this work is that the trigger point itself can potentially be calibrated on scientific evidence about, for example, what is the chance that the Atlantic circulation might collapse at a given temperature. And also, the other important feature is this, what you can see here, this slow ramp up in economic damages, rather than, say, an unrealistic, instantaneous falling off the cliff of economic output at a regional or global level. Nonetheless, I think it would be fair to say the challenge that this strand of research faces is in thinking about what is the magnitude of post-tipping damage, okay? There's really no ready-made evidence on which economists could calibrate this quantity. And therefore, the literature that uses this representation has to make a priori assumptions about how much GDP might be lost eventually, if not even instantaneously, when a tipping point is crossed. Our typical number might be 30% of global GDP. So, studies like this have been very helpful in answering questions like, suppose or assume crossing a climate tipping point causes an economic catastrophe, what then would be the best policy response? So you can, at least qualitatively, if not semi-quantitatively, ask the kind of questions that Anne-Sophie was asking earlier about whether precaution is an optimal strategy. But clearly, since you're making an a priori assumption about how damaging crossing the tipping point will be, you cannot then use this model to ask the question, what will be the impacts of crossing the tipping point? Because that would be circular reasoning. The impacts of crossing the tipping point are primitive in the model. Therefore, if we want to answer the second question, what would the impacts of crossing a climate tipping point be? Then we're going to need a different approach. And that's here we're going to need, or here we can be helped by the subset of economic studies that have actually tried to construct models with what we would call geophysical foundations. In other words, economic models of climate tipping points that have at least a reduced form representation of the key underlying geophysical relationships that govern the tipping point. So a good example of this, an example I usually give, is a paper by Nobel laureate Bill Nordhaus in PNAS in 2019, where he built a reduced form model of melting of the Greenland ice sheet, which he could calibrate on the underlying literature in ice sheet modeling on collapse of the Greenland ice sheet, and then take that module and put it within his DICE integrated assessment model. So we could therefore get a sense of whether his simulation of Greenland melt was well calibrated on the underlying scientific literature, and then connect that with a model of the damages from sea level rise. Now, the difficulty with this literature based on geophysical foundations is that it's fragmented. So there are 21 papers or so in this literature. Each typically takes an individual tipping point, and it employs a particular integrated assessment model, or IAM, with its own idiosyncratic structure to study it. So if you then want to somehow construct a synthetic estimate of the impacts of crossing lots of climate tipping points, you've got a challenge. You can't just take estimates from the literature and add them all up, because they come from different IAMs, and in any case, the effects of tipping points may not just be additive. We tried to overcome that by synthesizing the various studies using a so-called meta-analytic integrated assessment model. So we built replicas of the tipping modules in this literature, and then we nested it within a larger integrated assessment model, which is capable of thinking about the ways in which the tipping points impact on temperatures, sea levels, economic output, and interact with each other. These are the 8 different kinds of climate tipping point that we looked at in our paper. This list largely overlaps with the items on the chart I showed you at the beginning of my talk. You can see permafrost carbon feedback. The one that wasn't on the Armstrong-Mackay list, dissociation of methane locked up in hydrates or clathrates near the seafloor, just under the seafloor. Melting of Arctic sea ice, dieback of the Amazon rainforest, disintegration of the Greenland and West Antarctic ice sheets, slowdown of the Atlantic circulation, and variability in the Indian summer monsoon system. So what were the results of trying to synthesize these different tipping points in one model, in one study? So unsurprisingly, incorporating climate tipping points increases the economic impacts of climate change. So the metric here is the percentage change in the social cost of carbon. The social cost of carbon is an important metric in climate economics. It measures the present value of the damages caused by an additional 1 ton of CO2, and it's important in various policy processes. So the metric here is the percentage change in that. So how much higher is the social cost of carbon once tipping points are factored in? This metric, the percentage change in the social cost of carbon, it turns out that our results are pretty, this distribution you can see in front of you is pretty robust to a wide range of parametric assumptions, such as discount rates and so on. It means that if the social cost of carbon that you have in your mind is $50 a ton, then you can apply these percentage changes you can see in front of you to that. But if the social cost of carbon you have in your mind is $200 a ton, which is closer to the latest numbers coming out, then you can equally apply these percentage changes to that 200. So our best estimate, based on the literature we synthesized, was that climate tipping points would increase the social cost of carbon by 25%. But you can also see that the distribution is wide and has a long right tail. So we estimated a 10% probability that the social cost of carbon could be doubled as a result of climate tipping points, and a 5% probability that could be tripled. So if your base social cost of carbon is 200, then our best estimate is it goes up by another $50. There's a 10% chance it could be 400, and a 5% chance it could be 600. Okay, so 2 points here really. So tipping points increase the social cost of carbon, but they also increase risk. Okay. Another way of thinking about the fact that tipping points increase future risk is by looking at the distribution of global average consumption per capita. The blue distribution is without tipping points. The red distribution is with tipping points. Tipping points shift the distribution to the left, so they reduce people's incomes, and they also spread the distribution further to the left, so they increase the risk around people's future incomes. Don't pay too much attention to the range of the x-axis here, because that's this is quite a conservative formulation, and you can easily drive those numbers upwards with appropriate assumptions. The point is that tipping points make the future riskier. And from an economist's point of view, that's interesting, not just because it impacts on optimal climate policy, but it also has other macroeconomic implications. The last thing that we were interested in is what would be the distribution of impacts from crossing climate tipping points around the world. We were interested in whether they were concentrated more in some parts of the world than in others, and whether they were progressive or regressive. But actually what we found out here is that the increased climate damage is almost everywhere and did not have a material impact on income inequality across countries. So this seems, in other words, to be a shared problem. Let me make some concluding remarks now. So the first remark is that climate tipping points are a serious reason for concern, and they increase the already solid case for limiting global warming to a low level, particularly if we conceptualize the uncertainties as being deep or Knightian. And that's actually not something I talked about in this presentation. I tried to think about climate tipping points in a risk framework, but if we also acknowledge that tipping points may increase our second order uncertainty, then there is this issue to think about too. The second point I want to make is that the numbers I've presented to you in the latter part of my talk are probable underestimates, okay? Because, for example, the list of tipping points that we were able to include misses some. And also we know that some climate impacts are missing from the tipping points that we were able to include. So although it's, you can't be sure, it seems very likely that the numbers will go up over time as people continue to pursue this research program. It's best to see this as work in progress and be careful in drawing too many conclusions from the first attempts to model these things and to synthesize them. But having said that, as we move beyond thinking about tipping points as generic catastrophes in our models and move towards thinking about models with geophysical foundations and where crossing a climate tipping point generates tangible outcomes in terms of temperatures, sea levels, and so on, we could open out a set of decision useful insights for adaptation and economic policy beyond arguing about optimal temperatures, which is, as I said in my first point here, is an argument that I think has essentially been won, is done. So that is the end of my talk. Thanks very much for listening. I'm going to stop sharing and hand back over to Thomas.
Excellent. Thank you very much, Simon. And again, thank you very much, Anne-Sophie, for both the excellent talks, which I really think complement each other. Now we are now taking questions from both speakers, and maybe to kick off the discussion session while we still wait for some more questions to pop up, although there are already a few. I'd like to ask first a question maybe to both speakers. Anne-Sophie and Simon, you both have talked about, of course, risk. Different terms have popped up like ambiguity or uncertainty. And one could think of a few other types of, let's say, randomness in the dynamic system that might be of importance. Now, here's my question would be rather to both of you, when you look at your experience in your research, do you think that there is some type of randomness that might be strictly dominating other types that would be also, let's say, from a non-economist community be advisable to embed into models?
Good question. Shall I go first, Anne-Sophie? I'll give you. I'll sacrifice myself and let you formulate a more sensible answer while I go first. Well, okay. So I think when we build economic models of climate change, we have to pay a lot of attention to this difference between what some people call aleatoric and epistemic uncertainties. In other words, sort of broadly speaking, genuine noise and randomness, which is more a feature of economic systems in the short term, I guess. And we're familiar with building models where we have random and quasi-random shocks to things like productivity. And on the other hand, epistemic uncertainty, which reflects our lack of knowledge about the system. And I think broadly speaking, the latter types of risk and uncertainty are more important the longer the timescale that we've got in mind. So certainly when doing something like estimating the social cost of carbon, it's very important to try to properly capture the epistemic uncertainties and potentially to even try to quantify the known unknowns in the system on those long time scales. So that's my effort at answering the question.
Yeah, I'm bringing up this question since we are a very mixed group today, and not many economists are in here. And of course, the choice of the type of randomness that one includes into economic models does probably matter a lot for decision making and for the optimal policy. And Anne-Sophie, in your one of the slides where you talk about these different threshold of the regimes A and B, that you don't only have the system threshold, but also the social economic threshold. On top of that, you also have the risk threshold. So I was thinking, how far can that go? This is getting more and more complex, right?
Yeah.
How do you do the trade-offs for decision making?
So in our group, what we are looking at, because what we do is that we look at these issues as complex systems. So these are complex systems, and you have a lot of uncertainty or impossibility of assessing what's going to happen, because it's so many different dynamics that interact with each other that when you tweak a little thing, it can make a big difference on the outcome in the end. So I think that's one way of looking at that. I mean, that as even if you have a fully deterministic model, it may look very stochastic just because you have this complex adaptive system characteristic that makes it wobbly in a sense that you can end up in very different situations with very small change. And there are also other aspects of uncertainty that we haven't talked. I mean, we're now mostly focusing on the uncertainty in the natural system, but the socioeconomic uncertainties are huge. You have like strategic uncertainty in how people interact with each other, what choices they make in these interactions. And yeah, so there are a lot of uncertainties, and that makes the study of these things challenging, but also fun.
Yeah.
Perhaps.
Well, you talked about collective actions a lot, and I think that when we think about very, very high social cost of carbon that we might want to address maybe as a global community, then collective action might be very required, right? And if this is also subject to uncertainty, it will become more and more difficult. Great. Now we have a few questions, and I think one question that was Anne-Sophie, you had a question for Simon, right? You want to ask it yourself right now, or? Yeah,
I could ask it myself. So I've been working with some climate scientists, and they talk always about ensemble modeling, which is basically they use a lot of different models, and they when they want to make prediction, they don't give you a prediction from one model. They use a range of different models that they run with different parameters to give you a distribution of the prediction. And I was wondering if that has been done in economics, and was it a bit like what you were presenting from your research, or is it?
Yeah, so I think we do different kinds of things which overlap with what climate scientists do. So increasingly, one thing we do increasingly do as standard practice is Monte Carlo simulation of our models, which is, I think, ensemble modeling is sometimes described that way when we're talking about parametric uncertainty within one model. I know that ensemble modeling is also sometimes used to describe running different models with common input assumptions. That we do that from time to time, and that is something that we're moving increasingly towards, because as part of the efforts to estimate the social cost of carbon for the US Environmental Protection Agency, there's been this move to get various integrated assessment models on a common modeling platform so that they can be combined and recombined in a modular fashion. And so that, for example, you could take one simple climate model like FAIR and you could switch it for another one like MAGIC, or you could take one set of socioeconomic scenarios and substitute them for another. So it's model uncertainty in this way is something that we're getting better at dealing with.
Thank you very much. There is one more question in the Q&A section directed at Simon, I think, and regarding the effect of tipping points and the effect of tipping points across countries. The idea is that different countries have different abilities to adapt to impacts from tipping elements, and the question is whether this inequality in adaptive capacity might lead to higher impacts, of course, of tipping elements. How is this taken into account in the social cost of carbon analysis, for example?
Yeah, so the way we increasingly the way we model climate impacts is by it's not perfect, but I think it's an improvement on how we used to do it. We try to exploit the statistical relationship between climate fluctuations and economic outcomes in the past, different moments of the climate distribution and different timescales, and in so doing, across countries over time, we can capture differences in vulnerability. So when you do this, you typically find that the response of the economy to a temperature fluctuation is much higher in somewhere like Haiti than it is in somewhere like Germany. So the way we do this implicitly accounts for adaptation, and of course the thing that we need to rely on is that we can extrapolate out of sample, in the sense that the relationships we've estimated in the recent past will describe how economies respond to temperature, precipitation, and sea level rise in the future, which is not necessarily a watertight assumption. But the literature is at least a lot more evidence-based, I would say, than it has been in the past. I can see that the question here. I agree with the initial remark that the fact that climate tipping points did not seem to increase global income inequality is not intuitive. But there is a lot going on in terms of how climate tipping points change climate outcomes at the national level relative to climate tipping points not being crossed.
However, you also mentioned that the impacts of tipping points are very difficult to be estimated, right? So part of the impacts could be a growing inequality or migration patterns and so on. This is also very difficult, of course, to assess from economics.
Yeah, absolutely.
Now, one question that pops up immediately, because it's a very interesting one, is whether governments have come to you both for education and recommendations. You have both been working, I suppose, a lot with government institutions. Ever thought of doing education and recommendation?
So can I answer? At the Beijer Institute in the Stockholm Resilience Center, we have actually a program. It's a course for it, and it has been mostly directed to like CEOs of big companies. But this year it was also people from the unions, and the governments haven't come yet, but they should be also a target of this course. So we have a class, and it's not only. They are more educated about the tipping points and the global situation, not only climate, because there are other global environmental problems that are interlinked with climate that also are very important to discuss. So they get some form of education, and then I guess like Simon and me and any researcher who is in contact with some more official role, like I'm advising for the Swedish EPA, for example, then I can come with my perspective on these issues, and that's one way of doing it, but then it's not sure that it goes all the way.
Thank you, Anne-Sophie. Simon, your slide on the social cost of carbon distribution have sparked one question, while you are showing the percentage change in social cost of carbon and not the absolute value of the social cost of carbon.
Well, the percentage change appears to be really quite robust to a large range of input assumptions about, for example, discount rates, persistence of economic damages, and so on. The underlying quantity, the social cost of carbon, is less robust to these assumptions. So what I was trying to do was show you the percentage change and basically tell you, pick a social cost of carbon that you believe, almost without exception, I would argue that distribution would apply to that the set of assumptions you've chosen. Not always, but almost always.
Yeah, and maybe adding to that, in this study, you have combined studies that do the social cost of carbon assessment, both in, let's say, in a deterministic setting, but then also in a stochastic setting, right?
Yeah.
Okay, and so how is it fair to compare the social cost of carbon from both settings, since let's say we know from let's say individual decision making, when you are facing risk, you might be willing to pay a price for reducing the risk, or insurance, so to say. Wouldn't this so-called risk premium be also part of that distribution?
Yeah, well, I think it's a fair comparison, because we're sort of taking an underlying integrated assessment model, and we're simply adding a set of additional elements to it, at least some of which are themselves stochastic. So, risk will only increase doing that under reasonable assumptions.
Mm-hmm. Speaking of that, there's one question in the Q&A section that asks about the likelihood of tipping points that some of these tipping elements are dependent or might be interacting and occur simultaneously. So I have myself one work with Tim Lenton and Young-Yang Kai on interactive tipping points where we do this, but in the big reviewing study that you have conducted, Simon, were there other studies that looked into simultaneous occurrence?
No, because most studies just look at a single tipping element or think about the problem in a kind of stylized way. In our study, we did try to include all possible two-way and higher order interactions. But as it happens, we didn't find those interaction effects to be large.
Yeah.
But that is an empirical question.
Sure. And I mean, for economic modeling, this is a tough task, right? To, first of all, where do you stop, including how many? We also mentioned that we have not only global tipping elements, but also regional. That might be very difficult to incorporate. And okay, so there are a few more questions in Q&A. I think one question that popped out was, we talked about negative tipping points or catastrophic events or regime shifts. The question was here whether there are examples of positive tipping dynamics in social, economic, technological systems using equivalent methodologies.
Can I answer? I can. I mean, there are examples of positive tipping points in the social system. That, for example, social norms that can change relatively rapidly towards something different. I'm not sure. I'm pretty sure you don't use the same type of methodology to assess them, but I don't know if there are so many of these positive tipping points that have been observed regarding the environment, but you have, for example, the non-smoking. I mean, in Sweden, it was allowed to smoke everywhere in the 80s, and then it just disappeared, and nobody is smoking even outdoors sometimes now. So that's an example of positive change in social norm that could be an interesting tipping element that we would be nice to see also with regard to how we increase pollution that creates the climate change. So taking into account these possibility of positive tipping elements in the social norm can be a game changer for how to address climate change. The same with technology. There could be a new technology that gains a lot of leverage against the climate change that it could solve a lot of problems. But yeah, we haven't seen really that yet, but may happen fast. We don't know.
Thank you very much, Anne-Sophie. There's another question regarding the estimates of the social cost of carbon, while you know that they don't account easily for the damages impact for extreme events that are not linked to tipping points. Is there any work that tries to include those as well?
Yeah, I think we're moving towards that. So, as I said, we're increasingly working off historical evidence on the relationship between climate fluctuations and economic output. And in principle, that can be used in such a way that captures the effect of extreme events. It does depend clearly on the timescale of the fluctuations, the moments of the climate distribution you're interested in. But I think we're getting towards doing that more comprehensively. Yeah.
Very good. I mentioned at the beginning that our audience is quite heterogeneous when it comes to the scientific background. Now, myself, I've been also active in working together with non-economists on interdisciplinary work. you have a lot of experience working with non-economists. Would you be willing maybe to share your experience and on how you work, your economics work is perceived by the non-economist community, whether there are any challenges that you are still facing, and maybe you have some positive examples? I'm just asking because, you know, if we, let's say we have a young climate scientist or a young economist that wants to do interdisciplinary work, what advice would we give to her or him?
That's, yeah, I think the advice is to listen to each other. That's my experience, because when I started in this field, it's in many situations that meetings were really two opposing forces that didn't listen to each other and that disagreed on many things. But now I feel that in many situations we listen to each other, and then it's easier to understand where are the assumptions that we make that differ, that make us come to different conclusions, because that's what may happen sometimes. So I have now mostly positive experience of interactions with non-economists, and I'm very curious to see why they arrive to conclusions that are different than mine, and often it's because they have made different assumptions, and then we discuss, and then we can, that's where to start new research, right? Try to overcome the differences.
Simon, do you want to add on this?
I would agree with that. It's not always easy being a climate economist in the sense that sometimes we're seen as contributing more to the problem than actually solving it. I would argue that that's based on a misunderstanding of both of what we're trying to do and what's going on in the world.
Yeah.
But I could talk for hours about this. I think the only thing I would say to the people still on the call is that next time you read something online which engages in economist bashing, I would just take a deep breath and consider whether it's a fair account of what we're doing these days, why we're doing it, and how our numbers get used or not used in decision making.
Yeah.
And may I add also, there is also still, perhaps not so much among the scientific community, but there is still a big misunderstanding and a mix between the economy and economists. Because, I mean, there may be a lot of economic forces in society that drive the system towards a trajectory that is not desirable. But most economists who actually do research on these fields, they are just trying to make the world better, and it's not always easy. So I think that's also something to consider.
Thank you. There's a recent question to Simon's point. How do we know that the past experience is sufficient when the current climate is departing from the past 6,000 years of human civilization experience?
No, we do. It's a great point. I think actually a couple of comments in the Q&A are to the same effect. So we don't. But if we don't use evidence obtained from studying empirical data from the recent past, it's not clear how we would do it otherwise. Okay, so I would think that we've made big strides in the last 10 to 15 years in economics, because we've managed to get away from damage functions linking temperature with GDP, which were essentially completely made up, to ones that at least can be calibrated on the relationship between climate and GDP that's been observed over the last 50 years across the world. Now, for people like Andrew and Gabrielle, you can legitimately object that, well, that relationship may not hold in the next 50 years, but at least it's not made up. So then we can start thinking about how we might adapt that relationship to think about the future.
And if I can just add also, I mean, in this situation, there I think the past data, it depends a bit on how you use it, right? Because there are a lot of processes that remain the same, even if we are in a different climate. So if you use the data to analyze how these processes look like and what may push these processes into another regime, then you can get a lot of answers from past data. So, and just not using data from the past, it wouldn't make any sense, because then we have nothing to use, and we might as well just do nothing. That's also a choice, but.
There's one question in Q&A, actually the first one related to the work of Lontzek and others that seems to be me, together with Tim Lenton, Yongyan Kai, and Kenneth Judd on on the how we looked on the on empirical studies that look at the impacts. And in fact, as Simon points out correctly, the projection of temperature to GDP damages, and it was originally done in the integrated assessment modeling community. That's a very tough one, and that's like the largest layer of uncertainty when it comes to measuring impacts, of course. Now, one way that we have tried to maybe get around this is by modeling, not in that study, but there in this study we had a huge range of impacts. So we had some parametric uncertainty, and we ran the model a couple times, of course, to see whether the general behavior of the model would be robust. There was another study where we tried to have the impacts stochastic, where we didn't know, but still it's still risk, right? So we could assign probabilities and we could assign outcomes. There was no possible way of having other sorts of randomness, let's say uncertainty, ambiguity, model misspecification, any types of imperfect knowledge that Simon also referred to before, right? Great. So I'm scrolling through the Q&A section, and I think we pretty much answered most of the comments so far. I think one comment, yeah, I think so, unless there are some new questions showing up. Oh yeah, there's one by Gabby. A question about calibrating the models, but how do you account for tricky observed events that may or may not be climate related, such as some unrest that have been linked by some to climate? Isn't that a very wide range of possible sensitivities? Sure. I mean, we are talking about, maybe I should ask the speakers how to respond to this question.
Yeah, it's difficult. So the way that people have tried to do this nowadays is primarily using econometric techniques of identifying cause and effect. Typically panel data techniques. So the standard model here would say construct a regression where you regress either the level or growth rate of GDP in a country in a particular year against the level or change in annual average temperature in that country in that year and in previous years, and then you would include dummy variables or so-called fixed effects to account for unobserved differences across countries. And you can also deal with cross-country common time trends in a similar way. And then you end up using just climate fluctuations within a country as your source of identifying variation. So you're trying to control for everything else that might plausibly affect the GDP of a country, and just look at climate fluctuations, which over short timescales are plausibly random. So that if you follow me, that's how we try to establish cause and effect of climate on the economy these days.
Okay, thank you very much. I think we pretty much answered all of the Q&A section questions, and so I guess with a few more minutes remaining, I would like to give a huge round of applause and thank to our speakers again for their excellent presentations. Thank you very much, Anne-Sophie, and thank you very much, Simon. Many thanks, of course, to our audience, to all of you who are still online for your attention and the participation and the active participation today. I would just like to maybe say that there will be new events even this year. I think the first one coming up in two weeks. It has been posted online in the chat. And so I would also advise all participants, everyone online watching and following the webpage of our discussion series. New events will be announced on the website very soon. There is a link in the chat for that. So with that, I would like to conclude today's webinar and thank you to all of you for participation. Bye-bye.
Thank you.
Thank you. Bye.
Bye.